Okay, welcome back. We're going to talk about ancillary statistics in this section right here. This shouldn't take very long. I'll show you a couple examples so that you can get your head around things. I will at the very end of this discuss completeness and Basu's theorem, but we aren't really going to touch that in class. So I'm not going to test you on it. Perhaps at the very maximal, I might ask you for a definition. Define a complete stat. Tell me what Basu's theorem says. We're not going to prove it. And the reason why is because it has very little practical usage. There is something called conditional frequentism, where you condition on ancillary statistics, and you have to pick the right one, and there's no framework for doing that. So all I know is a few examples where an ancillary statistic can be of some use to you, but I wouldn't know how in principle to come up with which ancillary stats I would want to look at. Generally speaking, we care about sufficient stats. They are the things that have information about the parameters. I like minimal sufficient stats for reasons of computation and storage. Beyond that, everything is just kind of interesting at a mathematical level. So ancillary statistics are statistics that don't have any information about theta. So consider a set of xi's are coming from some model. This need not be IID. There could be some sort of dependence in here, but without any real loss of generality, you can think about all this stuff as IID for the time being. In spatial problems and temporal problems, they're not IID, and the same sort of concepts would apply. Okay, so S of x, so the book gives us a little bit new notation. S of x is our ancillary stat, where T of x is our sufficient stat. So this is ancillary. Or I might say an ancillary statistic if the distribution that I can form, so I take my original data set, I plug it into this function, I can figure out, at least in principle, what the distribution of this transformation. So this is just another transform. Some function of the data. This thing won't have any dependence on theta. Not a function of theta. So usually you would write in the theta, and then you might figure out what this is analytically and notice that there's no actual thetas that appear in the equation. And so that isn't there. So the distribution is not a function of theta. So this is its distribution. As opposed to saying that S of x is not a function of theta. Its distribution is not a function of theta. If you're building a statistic and you have theta in there, that is probably my biggest pet peeve. So you cannot use theta in your equations because you don't know it. That's the whole point of doing inference. So it's not that this isn't a function of theta. No statistic should be a function of theta. Its distribution isn't a function of theta, i.e. you can't use it to infer theta. It's of no use to you. So let me give you an example. And this is in your book. And it relates to the problem that we started studying very early on, about a month ago in class. So maybe pushing almost, a month and a half at least. So xi's are going to be uniformly distributed, but this is going to be a little bit different than the uniform distribution that we used last time. So this is going to go from theta to theta plus 1. The difference is is that I have a theta on the left and the right here. So this is of unit length, right here. I is going to go from 1 to n. Everything is IID. We can figure out what this distribution is, what the density looks like. So f of xi given theta just looks like this. Theta to theta plus 1. And I didn't draw this quite to scale because this should be a square. That's a 1 right there. So f of xi given theta is equal to 1. Now this distribution does depend on theta. It doesn't look like it when we write that down, but when we look at the bounds of support, we'd say xi's are between theta and theta plus 1. And so the question might be like, what is sufficient for figuring out theta? We could write this down, that x1 is bounded by theta, is bounded by the maximum, which is bounded by theta plus 1. And so I don't even need all of the data to define this constraint. Rather, we just need the min and the max. So that's my min, and that's my max. So I can rewrite this a little bit, and I can write down that xn is less than or equal to theta plus 1, and x1 is greater than theta. And I can rewrite that a little bit differently. So I can say minus 1 right there, xn minus 1. So theta is bounded by these, xn minus 1 and x1. So I might want to think about that. Let's just take a step and think about the factorization theorem. So this is always the hardest sort of problem where theta is on the boundary, and you always need to indicate that in your functions right here. So I could rewrite this a little bit, and I could rewrite that f of x cap x, so this is my whole collection of data, x1 to xn, doesn't need to be the order stats, given theta, is going to be equal to product, I goes from 1 to n, 1. And this would be wrong if I wrote this down right here. I'd need to have this constraint built into everything. And so what I'm going to do is I'm going to indicate that with a delta function. So I'm going to say theta is between the min, oops, wrong way. Theta is bounded by the max minus 1 bounded by the minimum. So this is just an indicator function. I could rewrite this slightly differently and everything if you'd like, and I could have written down this is the product from 1 to n, 1 times a delta function that the xi's are bounded between theta plus 1 and theta. So that's an indicator function saying that those xi's are bounded. Let me just rewrite that since it looks a little bit messy. So let me take another whack at this. Probably should just do it in order. Okay, so f of x given theta is going to be equal to product. I goes from 1 to n, 1 times my delta function, that xi is between theta and theta plus 1. So the way you read these delta functions is always the same. This is going to be a 1 or a 0, and this is if xi is between theta and theta plus 1, and this is a 0 otherwise. So it's a 1 if the argument is true, it's a 0 otherwise. So this part isn't really helping me with anything. So I can rewrite this using our other form. So this is going to be a 1, this whole function. I'm just producting together 1s if the constraint is adhered to. So if you told me thetas, you told me the xi's, those would all be inside of that unit interval. So this is exactly the same thing as just writing down, this is the delta function for theta. I like to think about it as a function of theta, so I usually write it just a little bit different. Xn minus 1 to x1. So this function is a 1 if that function is a 1. So this is a 1 if theta is in there. So I could tell you where I think theta lives in this interval right here. And it could tell me what theta is. So question is in the factorization theorem, what is G? G of Tx given theta times Hx. So this thing is equal to this by the factorization theorem, or Tx is sufficient. Where's the sufficient statistic? Well, it could be all of these data points in here, but I could compress everything and just use those. So these are min sufficient. So now I need to hold on to the max and the min. So I need both of those. I can throw everything else away. And it tells me everything I need to know about theta. So this thing is just the delta function. Function of theta and the sufficient statistics. Just happens to be min sufficient the way that I've written it down. So I did a compression and I jumped from writing the delta function like that to a simplified form. And H is just 1. So H can be a 1 in all of that. So we don't actually see any data, it's a function of the data, it's a constant, it's just 1. So that's what H of X would be. So that's pretty easy. So Xn, X1 are min sufficient. Okay, let's consider a transformation. So Sig transformation that we worked with early in the class, we're going to look at the range, and we're going to look at the mid-range. So the range is going to be the max minus the min. And the mid-range is going to be the average, arithmetic average of the max and the min. And so notice that our mid-range in our range is a one-to-one transformation of xn in x1. So one-to-one transform. So minimal sufficient statistic is a function of any other sufficient statistics. If I do a one-to-one transform of a min sufficient statistic, I'm not increasing its size, I'm not decreasing its size. There's a one-to-one mapping on everything. I'm not making it bigger or smaller. So these are also minimal sufficient. So minimal sufficient statistics are not unique. So R and M also minimal sufficient. So one-to-one transformations of min sufficient statistics are min sufficient statistics. So in our earlier example, Poisson, some of the xi's was min sufficient. Some of the xi's over n is also min sufficient because it's a one-to-one transform. The statistic that you usually work with to estimate theta in a Poisson is going to be some of the xi's over n. And that has some other implications because now I get to use the central limit theorem, which is kind of nice. So just little asides, little tidbits as we march through this. So also min sufficient. Let's look at the distribution on R. Now keep in mind this problem's a little bit different than the earlier problem that we got in the book, but the forms all look exactly the same. The bounds are just a little bit different. So I wrote this down. I think this is in your book. But let's just write down the joint distribution, F, R, and M, and we could derive this, but we've already done this before. Something very similar. So you can go back to that lecture, rewatch it, if you want to see this transformation of everything. So I need to first figure out the joint distribution of the order statistics, and then I need to transform. So, and I would get this. And we did this in class before. So this is going to be n times n minus 1. This is going to be r to the n minus 2. And that part looks exactly the same that we had before. The bounds here are slightly different. So r is going to run between 0 and 1. And the mid-range is going to look a little bit different. And it's going to involve the parameters. Theta plus r over 2. And this is going to be theta plus 1 minus r over 2. And I'll let you work through that. Just keep in mind this thing never goes negative right here, just because the interval length is 1 itself, and that's smaller than that. So that's the problem. And we could end up doing some integration and figure out what the marginal distribution of R is. So FR, given theta, is going to be equal to the integral of n minus 1, r, n minus 2, dm, where I'm going to integrate between theta plus r over 2 and theta plus 1 minus r over 2. And I'll let you work out what those bounds are if you'd like. Exact same argument that I used when I derived the bounds in class for the similar problem, but this was a 0 and that was a theta. Same idea, this triangular shape thing. So you can recognize this right here, these are linear equations, so we're going to have this other linear constraint that looks triangular. So very similar to our earlier discussion. And this integral is pretty easy to do. So there's no theta inside the integrand. So my favorite sort of integral to do is the one where I don't even have to work all that hard. So this is just going to be n times n minus 1, r, n minus 2, and then I'm going to end up just with these bounds right here. So theta, I'll give myself just a touch more room. So this is going to be n minus 1, r, n minus 2. I'll write down m, and m is going to live between theta plus r over 2 to theta plus 1 minus r over 2. So I can write that out. It's going to look like n times n minus 1 r to the n minus 2. This is going to look like theta plus 1 minus r over 2 minus theta plus r over 2. Here's the fun part. The thetas cancel. So I'll let you work out the rest. It's just, this thing is going to be 1 minus r. So we can write down what this distribution is in its totality. Give myself just a little bit more room. And this thing just looks like n times n minus 1, r to the n minus 2, 1 minus r. Remember, r lives between 0 and 1. So no dependency on the bounds. You would recognize this as a beta distribution. So this is a beta. And you could recognize which beta it is by writing this down as n minus 1 minus 1. And this is going to be 2 minus 1 right here. And so this is a beta n minus 1, 2 is how I would recognize that. This is just a normalizing constant. It comes in as the function of, well, it's a beta function inverted, which you can write down using gamma functions, which you can simplify because everything is integer in this problem. And it would end up being a simplification using factorials, and that's where this comes from. So a beta distribution. No dependency on theta. So there's no theta over here. It's gone. So the punchline is R is ancillary. So there's an ancillary stat, and I guess that makes sense. So I'll redraw this distribution right here that we were looking at, theta to theta plus 1. That's 1 right here. And so R is ancillary. So, and we could have intuitively figured out the range was going to be ancillary because theta is a location parameter. So theta is a location parameter. It's telling us where this thing is shifted to. So this is just a uniform of unit length that is shifting by theta. So theta is a location parameter. R tells us about the scale. I'll say it like this, has information about the spread of a distribution. It doesn't have information about a location. So that was almost intuitive, but we'd go through the mechanics mathematically, we'd derive its marginal distribution, and we'd show that theta doesn't appear. So I have a question. Does R have info about theta? And the answer is double-sided. It depends. So it depends on if I get to see M. So on its own, it does not. So answer 1 is on its own. No. But, answer 2, in the presence of M, yes. So, ancillary statistics can have information, but in the presence of something else. Basu's theorem deals with that. So what we'd end up finding out is that our min sufficient statistic is not complete, and there's a little bit of overlap. So how do we know that? Because we just already argued that R and M together are minimal sufficient statistics. So I can use those to get back x1 and xn. But if I just had R, I can't tell you what x1 and xn are, the order steps, the min and the max. But if you tell me M, the mid-range and the range, then I can tell you what the min and the max are. So I can just back transform them. It's a one-to-one transform. So there is information there about theta, but marginally there is no information. After we get through this, we'll discuss real quickly the notion of completeness. And in this problem, this sufficient statistic isn't complete. And so there's a little bit of overlap between the sufficient space and the ancillary space. What Basu's theorem is going to tell us is that if our minimal sufficient statistics are complete, then the ancillary statistics can never help us, even in the presence of anything else. So it's a technically nuanced point, because it's not what we actually do to do inference. Anyway, we'll come back around to that. So there's two answers here. And just to recap what I just said, so you don't have to rewind it too many times, in problems where minimal sufficient statistics are complete, then they're going to be independent of every ancillary statistic, and those ancillary statistics could never help you to do anything. That's not the case in this example, because the ancillary statistic R can help you in the presence of other information. Okay, enough said about that for now. So I want to show you a simpler example of this. So same sort of problem, but let's just do the discrete case so that we can enumerate all the possibilities. Working in continuums is a little bit harder because I can't enumerate for you. So I'm going to look at a similar problem. So this, I will say, is the discrete analog. So I'll say this is a discrete analog. To this problem. So I'm going to say probability, let me just make sure, I think they do this in the book. Okay. Probability that xi is equal to theta is going to be equal to the probability that xi is equal to theta plus 1 is equal to the probability that xi is equal to theta plus 2. No restrictions on theta here, so theta can go between negative infinity and infinity. Should probably take out those equal signs since it's just a concept. Okay, and this is going to be 1/3. So if I sum those things up, I get 1. So the probability of xi being different from any of those other values, theta, theta plus 1, or theta plus 2 is 0. I won't write that down since it's perfectly implied, since these all sum up to 1. And if we're following Kolmogorov's axioms, we can't add anything in, and we cannot subtract out probabilities either. Okay, so a very similar problem to what I just wrote down right there, except everything is discrete. So theta, theta plus 1, theta plus 2. One-third. So little bars in here. These should be equally distanced from each other, but you get the idea. They all come up there. So same sort of problem. I just want to show you that R does have some information, but I need to tell you what M is. So R can be one of three things. So R can be equal to 0, 1, or 2. So 0 if I sample twice from this. So let me just say, let's say we sample 2 times. So I'm going to say I is equal to 1 to 2, just to simplify everything. So only 2 samples in all of this. If the 2 samples are exactly the same, so if I drew twice from this, theta and theta, then R would be 0. If I saw one of those values was theta and I saw another one was different, and it came from this right here, then R would be 1. And R would be 2 if I ended up sampling from this and then sampling from that. So there's 3 possibilities on all of that. So let's just look at these. So R is equal to 1 cases. R is equal to, well, let's start with, well, we can do it this way. Let's just, yeah, fine. And R is equal to 0. So I'll just write out these different cases. So R is equal to 1. M could be any number of things. So M could be theta plus 1 divided by 2. So I could have drawn from here or there. Or I could end up drawing that M was equal to theta plus 1 plus theta plus 2 divided by 2. This is going to be equal to 2 theta plus 1 over 2, so this is going to be theta plus 1/2. This is going to be 2 theta plus 3 divided by 2 is going to be theta plus 3/2. So pretty simple arithmetic. Each one of these has probability 1/2. How do I know? They're all equally likely. So I could have seen that one or I could have seen that one. So this is conditional on R being 1. So let me just be real clear about that. So conditioned on R is 1. So the probability that I see this mid-range or that mid-range are equal, and there's only 2 possible cases where the range can be 1. So each has probability 1/2. R is equal to 2. There's only one possibility here. So I have to have that right there. So R is equal to 2. The mid-range has to be theta plus 2 divided by 2. It's equal to theta plus 1 with probability 1. And then we have this last case. Where M could be equal to theta plus theta divided by 2. So if the range is 0, we draw twice from each one of those modes. So maybe I see that twice. So that's this right here. So this is going to be theta. Right here, 2 theta divided by 2. This is going to be the mid-range, could be theta plus 1 plus theta plus 1 divided by 2, which is equal to theta plus 1. The mid-range could be theta plus 2 plus theta plus 2 divided by 2 is equal to theta plus 2. So each one of these could occur with probability 1/3. So if you told me that the range was 2, and you ended up handing me the mid-range, I would tell you with probability 1 what theta was. So I'd compute the mid-range and I'd subtract off 1 and I'd say, I'm perfectly sure that that is what theta is. However, if I saw the range was equal to 1 and you gave me the mid-range, then I could only be half sure of what I thought theta was. So I would say with probability 1/2, theta is equal to the mid-range minus 1/2, or it's equal to the mid-range minus 3/2. So, and I wouldn't be sure which one it was. So there's not enough information to lock down with certainty what the answer is. So the range does give you conditional information in this problem, but on its own it gives you no information. I think this problem is outlined in the book, so read through it and have a look. So that's about all I want to say about ancillary. So usually I'll just ask you on a midterm or something like that, show that this statistic is ancillary, or maybe pick an ancillary statistic and show that it's ancillary. What you would need to do is work through your transformation of variables, find the distribution of that statistic and show that thetas don't appear. None of the model parameters appear. So R does have some information here. Let me just talk very quickly about completeness in Basu's theorem. If I ask you anything about it in the class, it's just going to be for a definition. I did assign one problem concerning completeness, just so you can see that it's a difficult definition to work through. So, I'll say Tx is complete. I'll say is a complete statistic if expectation of g Tx is equal to 0. And this g function right here is arbitrary, so I need to think about all functions g such that this is true. So this is an arbitrary function. I'll say it's general. For general g's. So I'm saying if there is a function g such that the expectation of this statistic right here is equal to 0, that's going to imply that the probability that GTX, same function, so we don't change the g, is equal to 0 is equal to 1. So what this says is if the expectation of this thing is 0, then it is 0 with probability 1. Which says it is 0, except on a very tiny small subset that is unmeasurable. So on any measurable subset, it's 0 with probability 1. This is difficult to work through, because you have to prove this in general for any function g. I have to find all function g such that this is true, and then show that they all have probabilities that that function itself is 0. We won't go into all the reasons why Fisher came up with this, but he figured out that if, so I'll just write down Basu's theorem. And who's poor Basu? The only place I ever see poor Basu's name is on this theorem that I'm not even going to touch or talk too much about. It's interesting from a math standpoint. Very little practical value here. So Basu's theorem says if T of x is minimal sufficient, so if it's minimal sufficient, and we know how to show that, we work through a ratio and show that it's constant, if and only if the sufficient statistics are the same in the numerator and denominator. So what we talked about in the last lecture. So if T of x is minimal sufficient and it's complete, meaning that I take my minimal sufficient statistic that I found and I can show for any function g that has expectation is equal to 0, then the probability of that thing is 0. That there's not a function out there such that this thing is 0, but this thing isn't identically 0. So if I can go through the exercise and show that whatever the statistic is in a general problem, it's minimal sufficient, and T of x is complete, then T of x is, and this is what I said in class, is orthogonal. What I mean to say is independent. And so that's how I'm using this. They live in two different spaces that don't impact each other. This is going to be independent of all ancillary statistics. So this is an ancillary statistic. And I'm going to say this is a very strong statement that it's not just any old ancillary statistic. This is going to be true for all ancillary stats. What I mean is this. Is that I'll just call it f of tx, and any old ancillary statistic that you can think about given theta is going to be equal to f tx given theta times f sx given theta. These are different f's. They're all different because they're different statistics. So in this one, since it's ancillary, it doesn't have a theta right there, so it factorizes. So there's no information given by the ancillary statistics. They can't help you even in the presence of something else. Our example a moment ago showed that this wasn't the case. So something wasn't complete in that example. So the statistic that we're working with, R and M, that wasn't a complete minimal sufficient statistic because R gave us information conditionally. So there was some extra information that was being supplied. Again, not super useful. What I would really say in that problem is just give me the min and the max, and I'll tell you the best I can what theta is. That's what we normally do. But I sympathize with Basu and with Fisher that they probably thought this was true no matter what. That the ancillary statistics in the min sufficient statistics, one gives you all the information, another one gives you no information, that they should always factorize. Turns out it's not true unless you have completeness on your min sufficient statistic. So I guess that's interesting. It took me at least 5 years after learning this to think that that was interesting. I didn't see any really relevance to it other than I had another proof that I needed to work through and be prepared to do. We won't do that. So I just want you to know what this is. If I ask you on a final, state Basu's theorem, you'll just write that down. If I ask you what is completeness, you'll write that down. You have one homework problem in the solution manuals floating around on that thing, and probably most people are going to look at it and go, how would I have done that problem and verify that things are complete in another arbitrarily hard problem? And it's difficult because you have to do this for all G. So you have to argue very generally about what that G is. I've never done that in my practical problems. Every manuscript that I've written, I've used sufficient statistics. I used minimal sufficient statistics, but I never went and verified that they were complete or otherwise. There's kind of an extension to all of this. There's something called the likelihood principle. Mohammed's going to lecture on that on March 29th. When we come back to class, I'm going to jump straight into chapter 7 and we're going to do point estimation. So with that said, I hope you're enjoying the week. I will have the final out to you sometime on Friday. It might not be at 1 o'clock in the morning on Friday, so sleep in, and at some point during Friday, I'll have that emailed to you and you'll have a week to complete it. So thanks again, you guys, and I'll see you soon.